No, there's no live chat. Sorry. Okay. So back to this. Two examples of two-dimensional motion. One thing when I screwed around with this, I reformatted it. I think I took some space away. So we're going to have river problems and projectile motion problems. An example of a river problem is a swimmer crossing a river. There are going to be a lot of problems about swimmers crossing rivers. And the thing that makes that a river problem and not a projectile problem is that the swimmer is going to have a constant swimming speed and the river is going to have a constant river speed, so there's no acceleration. But then an example of projectile motion, which is not like a river problem, is a free throw. So when I say free throw, I'm referring to basketball. You could, and I would have said the arc of a basketball, but I'm saving space because I didn't give much. So with the basketball, it's going like this, and you've got acceleration in the y dimension and constant velocity in the x dimension, since we're pretending no air resistance. Given a right triangle of sides A, B, and C, and hypotenuse C, A and B, hypotenuse C, write an equation to find the length of C. So C would equal what? Square root. Square root of a squared plus b squared. That's going to be something you'll use a lot in this unit, where it's all about right triangles. And really, physics is full of right triangles because you've got to take vectors and break them up into x and y components. What's used to represent the magnitude and direction of a vector? What have I been drawing? Arrow. An arrow. And if you do it right, like if you really are trying hard, then you'll draw your vectors like this. There's h and there's c, and guess which one has a bigger magnitude? H, because it's longer. But I don't always do that in physics problems. I'll just draw arrows and then I'll write down what their magnitudes are, because you can't just spend time making all your arrows a perfect length. But the length is proportional to the magnitude. The huge idea from that video that we just watched, the horizontal and vertical components of two-dimensional motion are independent of one another. And this is a very useful big idea because you can't apply kinematics formulas to something moving on a curve. You can apply kinematics formulas to the up and down and the left and right. So if you take things that are moving on curves, they're really doing both. You just deal with one dimension at a time. One baseball is dropped from rest. At the same instant, another is thrown horizontally with no spin in a vacuum from the same height. Follows a curved path. Which one hits the ground first? Neither. Okay, now the figure on the right shows a dropped ball. And it shows, oh, I should have gotten rid of that comma. A drop ball and a ball that's thrown rightward. So this is the drop ball. This is the ball that's thrown to the right. For the thrown ball, for this one, is there acceleration in the y direction? Yeah, and you can see it. These vectors here, this is v0, and this is v. And I'm going to write v0 is not equal to v. These vectors get longer and longer and longer. Technically, the velocity is decreasing because it's in a negative direction and getting bigger. But if you, so yes. Is there acceleration in the x direction? No. If you look at this, I'm changing this to v0y and vy. v0y is not equal to vy. But if I do v0x, and here's vx, then they're the same. So I'm going to write down here, you don't need to. v0x equals vx equals average x. So x dimension is going to be really easy when we start doing problems where we break things up into x and the y dimension. Because if you know one of these, if you know the initial velocity and the x dimension, then you know the final and you know the average, but not so in the y. So acceleration in the x, no. The key to analyzing such motion is to resolve or separate the motion into separate x and y vectors which can be numerically added and subtracted with other vectors of the same dimension. That's what this exercise that we're going to do here is all about. That and trig practice. When a problem has zero acceleration in both the x and y dimensions, what kind of problem do I call it? It's further up the page. And I'm just going to put a little caveat. It's just in this class. I think actually Mr. Pennington and Mr. Chase came up with this name.
River.
A river problem. So if I say river problem, I'm talking about zero acceleration in the x and y. And then when a problem has zero in the x, but an acceleration of negative 9.8, I call it a projectile problem, or a projectile motion problem, because that's what projectiles do. So in the beginning, though, we're just going to take a step back and go over the mechanics of adding vectors to one another. And this first one, we'll do it a little bit differently from the way we'll do the second one, because I just think it's better that way. So number one says, find the resultant vector that's produced by adding vectors A and B. And in the later process, we'll start out by filling out this table, and then we'll draw something over here. And then there are going to be some where you can just make your own table, and then you can draw a picture. And then some other ones where you can continue with that. But in the beginning, you're given these training wheels. But we're not actually going to use these training wheels yet. We're going to do it with no training wheels and add the wheels, which is weird. So I want to add vectors A and B. There's vector A. There's vector B. I've already shown you how to add vectors. How do I add them? Tail to head to tail. So I can either put the head of A at the tail to B, or I can put the head of B at the tail of A, and either way is going to work. I'll just, on this diagram though, I'm going to draw A. And I could actually measure that in centimeters, and then I could do a scale drawing down here. But I'm just going to say A is 3 units. And then B is down, and it's 4 units. So it's like this. And I'm going to do something a little controversial here. I'm just going to write 4. This is always a weird thing in physics, deciding whether, should I call that negative 4 or should I call it 4? And usually the side I fall on is, if my diagram shows direction, I'll usually just do absolute value. So this is 3 to the right. That's positive 3. This is 4 down, which in your calculator in math, you would call that negative 4. But I'm just writing 4 and showing that it's down. Okay, so these are my vectors. I want to know what the resultant that I get when I add them up. How do I do that? Well, how do I draw it? Tail to head. So you add these up head to tail, and then you go from the tail of one to the head of the other. And I like to think of this as trading in a couple of crooked vectors for a straight one. It's like if I were telling you how to get to here, and we were standing there together, I could say walk 3 paces to the east, and then walk 4 paces to the south. Or I could just point in this direction, and I could say walk how many paces? 5, because this is a 3, 4, 5 triangle. You could find the magnitude of this. You could do with square root of 3 squared plus 4 squared, which ends up being 5. Probably just recognize that as a 3, 4, 5 triangle. So we've drawn it. We've got the magnitude of it. The direction of it, this is where we've got to do some trig. There's no way around it. So in your pre-calculus classes, you're going to have a certain kind of notation for describing this direction. If this is the origin right here, like, I don't even know how they do it, because in here we're flexible. What we do is we pick a landmark, and we tell how many degrees it is away from the landmark. So this I'm going to call the positive x direction. And this I'm going to call the negative y direction. And this is the positive y direction. And this is the negative x direction. And I can think of a couple good ways to describe that. I could either say it's this many degrees below positive x, or I could say it's this many degrees to the right of negative y. That makes sense? So since I've drawn my triangle like this, since I drew the A first and the B second rather than the B first and the A second, I've kind of got this angle, so I'm going to find that one. So we need to find, I'm going to call it theta just for consistency. We need to find theta. How do we do it? Using trig. So yeah, to get an angle, you've got to use an inverse function. And if I look at the two numbers that I have, I've got the 4 and I've got the 3. What leg of the triangle is the 4 if this is the angle? Is it opposite? Is it adjacent? Hypotenuse? What is it? Opposite. It's the one opposite this angle. So we've got the opposite. And which leg is that? Adjacent. So opposite and adjacent, that's the TOA part. Tangent is opposite over adjacent. So just for good measure, I'm going to write tangent of theta is 4 over 3. So if I want theta, theta is going to equal the inverse tangent of 4 over 3. So try that on your calculator. If you don't have a calculator, get yourself a calculator. And then you can compare with me. So I'll do tangent 4 divided by 3. Oh no, I screwed up right from the beginning. Should have done inverse tangent. Second tangent 4 divided by 3. Are we out of calculators? So it's 53.1. That's what I get. See? Are you getting that? Yes. Okay. So this is 53.1 degrees, and I'm going to write 53.1 degrees. So what is it? 53.1 degrees to the right of negative y or below positive x? Below positive x. Below positive x. Now I could have defined, if I had wanted to do it in degrees to the right of negative y, what would it be then? It'd be that. That's just 90 minus 53.1. So it'd be I could say this is a 36.9 degree angle. I could say it's 36.9 degrees to the right of negative y, and that's just as valid. So we did this without even bothering with this little table. And most of the time for a problem like this, you don't really need the table. This is what's called an orthogonal problem, or at least what we call an orthogonal problem. Does anybody know what the word orthogonal means? It means right angles, left and right, up and down. So we had a vector that was going to the right, and we added it to a vector that was straight down. There's nothing at any weird angle. This next one, though, is going to be non-orthogonal. It's going to have funny angles, and it's not going to be as straightforward. So we're going to need this process. So let's do this process anyway that I didn't do. So the vectors are a and b, and the first step is for each of the vectors for a and b, write down what the x and y components are. So there's a. Which component does it not have? It doesn't have a y. So the y component is 0, and the x component is 3. Yeah. So 3, I'll put positive in there, and 0. And b, does it have an x or does it have a y? Y. Just a y. What's the y? -4. And this will be 0. So you can take these, break them up into the x and y components, and just add up the component vectors, and then you get 3, -4. And that gives me the x and y component vectors of the resultant. And that's kind of what I've drawn. I went over 3, I went down 4. I could go down 4 and go over 3. So it seems kind of silly to do this on this one, but this next one it won't. Let's go to the next one. We need to add vectors e and c. So write the x and y components of e and c. And I'll give you a little time to try it. There's e, there's c. Okay. As soon as you're done, check and see if you got what I got. That's what I get. -3, -4 for E, and +1, -3 for C. E goes to the left 3, so that's the x of -3, and it goes down 4, so that's the y of -4. C goes to the right 1, so x is +1, and then down 3, so y is -3. All right, the totals. What's the total for the x components? -2. And for the y? -7. So these are the x and y components. Like these are 3 different ways to talk about the answer to the question. When we add these 2 vectors together, we get a vector with these x and y components, this magnitude, and this direction. So now I'm going to use the x and y components to draw it. I'm going to start from the center. Do you want me to do the x or the y first? Anybody care? I'll just be weird. I'm going to do the y first. I'm going to go down 7. So let's assume that's 7. And this is this right, y. And then I need to go do the x, so I'm going to go over 2. Here's my x. Oop, I'm running into the other space. And like I told you, I'm just leaving 7 and 2, even though this is really -7 and that's -2. And then the resultant is like this. And I don't know if I've drawn these to scale. If you got a ruler out and you actually made this 7 units and this 2 units, then you could just get a protractor and you could measure that angle, and it would be the right answer. Okay, so has anybody figured out the magnitude? 7.28. Yeah, it's the square root of 2 squared plus 7 squared, which is so I'm going to call it 7.3. And now the direction. Because of the way I drew my triangle, that's going to affect the way I describe the direction. If I had done it like this, if I'd gone over 2 and then down 7, I'd have a triangle that looked like that, and I might be tempted to get this, but I'm just going to go with this one. So there's theta. See if you can calculate what theta is and then write the direction there. I'll give you a little time to do it, and then I'll do it. Okay, what'd you get? 15, so about 16? Yeah. So since this is the angle and this is the opposite and this is the adjacent, opposite and adjacent, that's tangent. So the tangent of the angle equals 2/7, which means the inverse tangent of 2/7 equals the angle. So second tangent 2 divided by 7, 15.9. I'm going to call it 16. So the answer is 16 degrees, but I wouldn't get full credit for that because 16 degrees where? Above the horizon? Yeah, so since it's closest to -y, I'm going to just say imagine -y and then swing to the left of it. So this would be left of -y. And what's another way to express that? Instead of 16, I could call it 74 degrees. What of what? Below -x. Here's the -x axis. All right. So that's a non-orthogonal problem. Later on, the trickiest river problems that we have are going to be non-orthogonal. They're going to be things like a helicopter is flying in a wind that's 32 degrees east of north at 5 miles per hour, and the pilot needs to get to a location 200 miles away, 40 degrees north of west, in a time of 3 hours. What direction does the pilot need to head, and how fast does the helicopter need to go through the air? But it's really just doing this. It's going to seem much more complicated, but if you can do this, you can do that. Chris?
Instead of doing like the left to negative y stuff, can you just do south 16 west?
Yeah, that's fine. But if it's on a map, for sure. But on here, if you want to check your answers, they're all this other way. So make sure you can tell if you're right by looking at that. Okay, so number 3, let's kind of do it together, but not entirely together. You're just going to need to make a chart and then do all this without being given the chart. So I'll start you out. We need to find x and y components of D and C and A, and then after getting those, we get the totals, and then ultimately we're looking for the magnitude and direction of the vector that you get when you add them all up. So this would be kind of like asking you, if somebody's in a river that's flowing north at a rate of 5 meters per second, and they're heading in this direction at a rate of 3 meters per second, and at the same time the river is on top of a continent, and the continent is moving like this at a rate of 3 meters per second, which way are they actually going and how fast? Be a fast continent. So try that. If you, I'll show you my answers in just a minute. If you want any help or you want confirmation coming around. If you are done with this and you want to just knock out number 4, 5, and 6 real quick because it's easy for you, go ahead and do that. And if you want any hints, you know. Looks like everybody's on track. Just going at different speeds. I'm going to start writing some of mine down, so if you want to check your work, you can. All right, so when I did it in the other class, this was the way I did it. At 0 and 5 for D. Oops, sorry. Yeah, so it doesn't have any X component. Positive 5 for Y. I'm not going to go over all those because I think people get that. So 1 and -3, 3 and 0. So the totals were 4 and 2. So these are the X and Y components of the answer. And when I did it in the other class, I drew the Y component first, positive 2, and then the X. So I got this triangle right here. And to get 4.47, I used the Pythagorean theorem. I did 2 squared plus 4 squared, took the square root of it. It's about 4.5. And then for this angle, I said that tangent of the angle is 4 over 2. Therefore, the inverse tangent of 4 over 2 is, is the angle, which equals 63 degrees. In this class, I did it a little bit differently. I drew my triangle like this. I went over 4. This is probably how most people would do it. Did the X first, then the Y. So the tangent of this angle is 2 over 4. And so the angle is the inverse tangent of 1/2, which is about 27 degrees. So if you give this angle, it's 27 degrees above positive X, or if you look down at the answer key, 26.5 degrees above positive X. And if you give the other answer, it's going to be about 63 degrees right of positive Y. Anybody have any questions about that stuff? So you're